Hello everybody, and welcome to the next lecture of 6838. Now, unlike many lectures in 6838, today we're going to cover a problem which really the main interest is abstract. So rather than applying mostly to two-dimensional surfaces like what we might find in computer graphics, today we're going to cover a topic that's more relevant to large-scale optimization and related topics. Now, the main topic that we're going to talk about today is optimization with a manifold constraint. Now, here's the high-level point. So many different problems in machine learning, computer vision, and almost any other research discipline that has some computational component involve optimization problems, and many of them can be written in the form that I've put on the top of the slide here. The basic point is that we have some variable x, where x is constrained to be in some manifold M, and sometimes that's actually our only constraint, and then we have some functional that lives on that manifold. And there's so many different manifolds out there that represent the constraints in different computational problems. Now, obviously, 99% of our problems are unconstrained, and so probably the manifold implicitly is Euclidean space Rn. But other times, maybe we optimize over unit vectors. So for example, the unit sphere, Sn minus n, is the set of vectors in Rn that have unit length. We can talk about the Stifle manifold, which is the set of orthonormal k-frames in Rn. So in other words, the sets of orthonormal vectors in groups of k in Rn. So like if k equals n, this would be a set of orthonormal bases. There's the Grassmann manifold, which is a set of linear subspaces, the rotation group, the set of semi-definite matrices. And it turns out each of these sets is itself a manifold in the usual sense of the word that we've discussed quite a bit in this course. And so what we're going to do is we're going to use the structure of that manifold to define interesting optimization algorithms that can accelerate computation in different domains. So, for example, one very common problem in computer vision is structure from motion, where maybe I observe some 3D object from many different angles, and now I want to sort of put all of these different camera poses into one common frame. Well, then I have a search space, which is maybe the set of rotations or the set of rotations plus translations, which is going to be some pretty straightforward manifold. And that's essentially my set of variables, right? Because I'm trying to position each of these cameras given maybe a signal about the relative motion from one into the other. Another topic which is close to my heart that has a lot of manifold constraints is cryo-electron microscopy, or cryo-EM. So cryo-EM is a really fun research discipline. Essentially, you're trying to image some macromolecule. What you do is you freeze it and put it into an electron microscope. So in particular, let's say that I have some protein and I'm trying to figure out its structure. And it doesn't crystallize or do any of the nice things that like DNA did back in the day. Well, one thing I can do is take a sample of my protein suspended in fluid and freeze it to a very low temperature, which essentially stops it from moving around inside of the fluid. Now I can take a razor and shave off a very thin layer off of the top of that block of ice. Now, when I put that into the electron microscope, I get some image like what you see on the upper left here, which basically looks like noise. But hiding in that noise is a tiny, tiny amount of signal, which is an image of the protein. But the problem is that you don't get a 3D picture of the protein. You get a picture of the protein kind of projected into the plane of the camera. Now, we don't have little itty-bitty tweezers that get to rotate this protein around so that we can take different pictures of it from different angles. So essentially what ends up happening is that the protein is suspended in this fluid and stops moving when it's frozen, and then you image it, and what you get is the projection onto the image plane at this random angle. Now, if you have a big sample, then you get images of the protein at a bunch of different angles, maybe like what you have on the upper right in an ideal universe. And your task is to reconstruct the geometry of the protein from these extremely noisy projections. So in this case, you have a bunch of manifold variables, which again are basically the unknown rotation angles of the protein when they were imaged. And then once you know the rotation angles, reconstructing the actual image of the protein is a glorified linear system of equations, right? It kind of comes from similar math to like the MRI device or anything else with a bunch of line integrals into a plane. So cryo-EM is another great example of a problem with a lot of manifold constraints. Here's yet another one, which is sensor network localization. So in this case, maybe I have a bunch of cell phones and they all talk to each other. And each cell phone can measure the distance to some other set of cell phones, like this graph you might see here. And then my goal is to essentially reconstruct the cloud of positions of all the cell phones, given these noisy pairwise measurements of distance. Sounds an awful lot like the MDS problem, which also kind of fits into this framework. But in this case, what is our manifold? Well, it almost feels like maybe r to the 2n, where n is the number of points, and the 2 maybe is because we're in the plane in this particular case. But if all I do is measure pairwise distance, then I have to quotient out rigid motion, like rotation and translation, and that gives me some other manifold that isn't quite r to the 2n anymore. So that's just to give you some flavor. Essentially, there's so many different computational problems that can be understood as optimizing on some manifold of constraints. And I think the really typical examples are the ones we saw here. So either manifolds that are basically the sets of points quotient out by some symmetry, like translation, rotation, or things like SO3 or a sphere, like basically, kind of spherical spaces. I think these are all really simple examples of manifolds where we typically have variables in vision, learning, and related problems. We'll see a few more in this lecture later on. So let's say that I want to solve one of these problems in practice. Again, I have the min over some variable x on a manifold M of f of x. Well, one thing that I can do is I can try to embed my manifold in a larger space and then write my problem as a constrained one. So for example, let's say that I'm working in the space of orthogonal matrices. Here, what is the set SO3 of orthogonal matrices? Well, they're matrices R, where R transpose times R is the 3 by 3 identity matrix, and for which the determinant is equal to 1. So what could I do? Well, I could say, okay, I'm going to expand F to be a function on the set of 3 by 3 matrices. That's a 9-dimensional space. But I'm going to add a bunch of equality constraints to my optimization problem, right? That my variable R has to satisfy these two relationships written underneath the min on the right. So what did I do? I took my nice manifold constrained optimization problem on the left, and I made it into just a typical constrained optimization problem on R9 on the right-hand side. That's a very typical thing to do. But here's the problem. That constraint, that set of R's that satisfy these two relationships that I've written on the right-hand side, it actually cuts out a really complicated manifold. It's a non-convex set, it's curved, and essentially it's cut out by a bunch of degree 2 and 3 polynomials, which you can write down just by expanding those two constraints there. And it is possible to embed this thing in different ways. Maybe you use fancy coordinates like Hopf fibration or Euler angles or whatever. But basically, the challenge remains here that somehow what you'd really like to do is just find a variable on this manifold and never leave it. But your optimization problem, the way you've written it here, has to deal with a much larger space, which is a set of all possible 3 by 3 matrices. And this can cause a lot of problems. For instance, for some objective functions, they simply might not make sense for a general 3 by 3 matrix, right? Like maybe I want to read off some angles from R, and I can't do that if R multiplies everything by 2, right? But somehow the way that I've formulated this problem here, maybe I would expect F to be just extrinsically differentiable on all 3 by 3 matrices instead of just on that manifold that I care about. And so in general, there's this sort of fundamental disagreement that happens when I write optimization problems this way, right? So what did I do? I took my optimization over the set of 3 by 3 orthogonal matrices, and I wrote it in the form like what you have on the right, where X is now some variable in Euclidean space, but it has to satisfy a bunch of really complicated nonlinear equality constraints. So if you kind of go back to the schematic that we drew all the way back in lecture 2 when we were motivating Lagrange multipliers, you end up in kind of this funny scenario like what I'm drawing you on the slide here, where now my objective function f is maybe defined on the whole space, not just the space of 3 by 3 matrices or whatever manifold that I'm working on. So what happens? Well, if I wanted to decrease my objective, in other words, I want to move maybe in the minus gradient direction, like what I'm showing you in this gray arrow here, well, that direction doesn't really act compatibly with the directions that I can move and maintain this g of x equals 0 constraint. And so at the end of the day, these two things are competing with one another. So, for example, what could I do? I could use algorithms like step and project, which take a gradient step on f and then project onto my manifold. And what I'll get is some optimization path, like what I'm showing you on this slide here. And this can be really problematic for a lot of different reasons. For one, somehow it feels inefficient, right? I'm spending a lot of computational effort moving out of my constraint set. And moreover, projecting a point to its closest point on this crazy curved constraint set may actually be a pretty complicated problem in itself. Well, given all the discussion we've had in 6838, it comes as no surprise that there's another way out of this problem. And essentially, it's motivated by exactly the same geometric structures and constructions that we've done earlier in this course, but now rather than applying them to 3D surfaces or something, we're going to apply it to the manifold that is cut out by the constraints in our optimization problem. So the basic perspective is a word that we've seen a lot in this course. Essentially, we're going to try and do optimization from a purely intrinsic perspective. Now, what does that really mean? Essentially, what it means is that our optimization constraints are cutting out some interesting manifold, like in this case, I guess the Mobius strip on which Mario is driving here. And that is really the only space that matters when it comes to optimizing my objective function. I don't care about the values of the objective function off of that set. And so we can derive a whole new class of algorithms, this is sometimes called manifold optimization algorithms, that essentially are sort of carrying out optimization like you're a ladybug that only knows how to move along your constraint set. So, let's say that this ladybug here is trying to find some tasty plant matter in the interior of this leaf here. Assuming that the ladybug doesn't fly off of the surface here, what can it do? Well, it's constrained to walk along this two-dimensional manifold, right? This curved surface worth of different directions in order to optimize this objective function, like to walk toward the nice smell. And essentially, our optimization techniques that we'll talk about today follow a very similar strategy, where what we're going to do is to find an intrinsic approach to optimization, which instead of moving along straight lines the same way that we might do in gradient descent, right? Gradient descent just hops some finite amount along a gradient vector. We're instead going to take curved paths. Right? So for example, in the picture on the right, if I'm optimizing some function and I have a constraint that my optimal point has to be on the sphere, then rather than taking a gradient step in a straight line, which is shown in solid black here, I might follow a curved path, like a great arc on the sphere, like what's shown on the dotted curve. In some sense, what we're doing is saying that actually our optimization problem isn't, optimize a function x subject to the constraint that x is on the sphere. Instead, it's just kind of redefining the variable and thinking of this as some kind of an unconstrained problem, right? We're just saying optimize on the sphere this objective function, and our algorithms don't even know that there's a whole space around the sphere that they could work in. And this can be useful for a lot of different reasons. I mean, for one, it's an interesting math problem just to see if we can figure out what it means to do gradient descent on a curved space. But moreover, it turns out that it can often lead us to very interesting techniques that are more efficient in practice than the more general kind of constrained optimization algorithms. So here's our basic starting point. This is, I think an optimization algorithm that we all know and love, known as gradient descent. The basic idea here, of course, is that I'm trying to optimize some function f of x. So I iteratively improve x by moving some distance alpha k along the gradient at my current iterate xk. And as we all know, of course, if you choose an appropriate sequence of alphas, then this kind of algorithm for sufficiently differentiable f really does converge to a local optimum of our function here. So this algorithm implicitly is assuming that our variable x lives in n-dimensional Euclidean space, right? Because that's the space that we all know and love from calculus class and college level optimization. But one question that we might step back and ask is really, what are the constituent parts of this gradient descent algorithm? Like, what's making it tick? So, essentially, let's go back and take a look at this gradient descent formula and see if we can think about it in a bit of a geometric fashion. So here's my attempt to do so. Essentially, our formula kind of has two different interesting aspects to it. One is we need to be able to compute gradient directions for our function f. Like, remember earlier in this class when we talked about the Laplace operator, we talked quite a bit about what it means to compute the gradient of a function where that function is only defined along a manifold, like a surface. So that's the first thing, is given xk, we need to be able to figure out a direction in which to walk along our manifold, probably a tangent direction, that points in a direction of descent for our optimization objective function. And then the other thing that we need to do is actually walk along our domain, right? So we can think of this minus sign here as basically moving along a straight line in Rn, which of course we can no longer do if we're constraining every step of our algorithm to only know about the intrinsic structure of our constraint manifold. Now, I think given that you all have made it this far in 6838, you probably could take this formula and translate it into a meaningful optimization algorithm on a curved manifold. And my bet is that we would all choose some formula that looks something like this. Now, in our lecture on defining the Laplace operator, we actually told you how to compute the gradient of a function on a manifold. So we can leave that gradient computation the same. Right? So if xk is on a manifold, then this gradient, grad f at xk, is some tangent vector to our manifold. But here's the problem now. I can't step along the tangent vector because that could leave the manifold. In fact, my manifold isn't embedded in Euclidean space. It's not even clear what that means. But if you think all the way back to our lecture on geodesic distances, we actually define an object that can help you get around this issue, and that is the exponential map. Remember, that's notated x at xk. And what is the exponential map? Well, it takes two things. It takes this point on our manifold that's in the subscript, and it takes a tangent vector at that point, right? That's what's inside of parentheses here. And what does it do? It moves along the geodesic curve on our manifold, starting at xk, in this minus alpha k grad f direction for a distance that's equal to the norm of that vector. Right? So if you take a look at this picture of the sphere here, essentially what it might do is start at a point P, receives a tangent vector which is pointing parallel to this red curve here, and then move along that tangent vector to reach point Q. So rather than taking steps along straight lines like the classical gradient descent algorithm, our first order manifold optimization technique just replaces that minus sign with the exponential map as shown in the formula below. Now, this seems like a pretty cosmetic change, but there are many reasons why we might like it. Now, from a practical perspective, this could lead us to better algorithms, right? For instance, we don't need to wait until the limit of convergence for our iterates to satisfy maybe very complicated constraints, right? Now, our constraints for our problem are automatically satisfied at every single k, right? Every single step of our gradient descent procedure because our procedure doesn't know how to violate the constraints in some sense. Moreover, from a theory perspective, it's a really elegant theory to talk about gradient descent on a general manifold. You can generalize notions like convexity, which actually depends a bit on the curvature of your space, gradient descent, Newton's method, and so on. All of them have nice analogs on curved spaces, which are useful to derive and actually show up in practice. Now, we're only reserved one lecture in 6838 to talk about this entire discipline from a high level. If you're interested in these sorts of topics, might I forward you to a really nice textbook. This is Optimization Algorithms on Matrix Manifolds, which covers a lot of these sort of manifold optimization techniques specialized to manifolds that are sort of subsets of the n by n or n by k matrices, which are what shows up in linear algebra, numerical analysis, statistics, and other applications. From a more practical perspective, there's a really nice MATLAB toolbox out there called ManOpt, which stands for Manifold Optimization, which abstracts away a lot of the headache of doing optimization on a general manifold and makes it basically a plug-and-play sort of technique for a lot of the common manifolds that we encounter in practice. And finally, my colleague Nicolas Boumal just recently released a book on optimization on smooth manifolds, which covers a lot of these things much more formally and in a great amount of detail, and in a pretty clear and intuitive fashion, which is a nice combination. Okay, so we're going to spend a little bit of time at least defining the most basic manifold optimization algorithm, right? That gradient descent technique that we've actually already seen now. And then do a bunch of examples just to kind of give you guys a flavor of what it feels like to do work in this particular area. So in order to do that, we need to review a few notions. So first of all, once again, for the nth time in this course, remember that the differential of a function is sort of our analog of a directional derivative. And actually what we proved is that hiding underneath the differential is a gradient to our function, which essentially can be written in this expression here, that like if I take the directional derivative of f at x0 in the v direction, that's the dot product between v and the gradient, or more generally the Jacobian of our function. We also talked about the tangent space of a manifold, which we actually showed there are sort of two equivalent definitions, right? One is that the tangent space is the set of tangent vectors to curves through a given point P, and that's the same as the image of a local parametrization after you differentiate it. Okay, so let's go back to our sort of optimization analog here. And now we essentially have all of the objects that we need, right? So in order to compute the gradient, what can we do? Well, we have the differential of f, and actually in our lecture on defining the Laplace operator, we showed that hiding behind every differential is a gradient vector. And the exponential map is just solving the geodesic equation, right? So in a little more detail, if you'll recall, we actually proved a proposition a few lectures ago that says, given a function f at every single point in our manifold, there exists a unique vector which is tangent and kind of acts like the gradient of our function. That's what defines this grad f in our gradient descent formula. And then if you go all the way back to our discussion of geodesic curves, we actually defined this exponential map x pure, which is essentially what happens when you solve this geodesic ODE starting at a point P in the initial direction V for 1 unit of time. Now, there's one complication from a practical perspective, which is that in this area of research, we're not working with general manifolds, right? There are like very specific manifolds that tend to come up quite often, right? Like the unit sphere, the manifold of orthogonal matrices, and so on. This is not just like a general surface, like a bunny or a cow that we're trying to analyze. And so oftentimes what you really hope for is a closed form exponential map. Sometimes that's possible and sometimes that's not, right? I think a very high level takeaway from our discussion of geodesic curves from a long time ago is that geodesic curves are complicated, right? They satisfy this crazy ODE, and they're often hard to compute, especially on general spaces. But one of the nice properties of manifold optimization, and in particular this first order gradient descent technique, is that you actually don't need a perfect geodesic. It turns out that there's a weaker notion which is perfectly fine and has similar, if not identical, convergence properties to manifold-based gradient descent. And that is that we can replace the exponential map with this weaker object called a retraction. Now, if you take a look at the definition on this slide here, this goes into detail on what a retraction is. Essentially, it's, if you were to squint at the definition here, you can see that retraction basically acts very similarly to an exponential map. And in this definition, you can see precisely what it satisfies. The first property, property 1 here, says that the retraction, which is a map that takes, is centered at a point like the subscript xk here, and takes in a tangent vector to the manifold, and then outputs another one. it satisfies two properties. The first one is that if I put in 0 into my retraction, it leaves that point alone, just like the exponential map, right? If I put the 0 tangent vector into the exponential map, it just gives me back the point that I started with. And the second property here is that if I differentiate the retraction at 0, then I get the identity map. And the reason for that is essentially what it's saying is that locally a retraction is isometry. So to first order, retraction and the exponential map agree. But then, as I move farther away from the center point, my retraction may no longer look like a geodesic curve. Right? So in other words, like, here's the picture that you should have in mind. So like, here's my manifold. And here's my point P. So remember, the exponential map takes a tangent vector, right, like V, and it gives me back a geodesic whose length is the norm of V and whose initial tangent is the V direction. So maybe some curve like that. Then basically, this definition of retraction says that if I put V into the retraction instead of into the exponential map, as the norm of V increases, well, initially it has to agree with my curve, but then they might diverge later on for bigger norms. So like just locally on the tangent plane, these things agree to first order, but then on larger neighborhoods they don't. And from a high-level perspective, you can kind of understand why retractions are probably sufficient for manifold gradient descent, which is that, gradient descent is a first-order algorithm anyway. So it just kind of turns out that as long as I agree with gradient descent to first order, all of the nice properties that I care about more or less carry through. All right. So it turns out that many manifold optimization algorithms are actually defined on a more general object known as a Rimanian manifold. I promised that we would at least touch on that in this course, and so here we're going to see it again. So remember, all the way back from lecture 1, our basic inspiration for Riemannian manifolds is this picture here. Now, we can define a manifold topologically as just a space that locally looks like Rn. So a manifold M is a set where, every single point there exists a diffeomorphism into a neighborhood around that point from, some Euclidean space Rm. And then a Riemannian manifold says that every point I'm going to attach a positive definite function on the tangent plane. I'll call it G, which gives an inner product. And the basic inspiration, as shown on this map here, is that I can use this rectangle to essentially represent a map of the world. That's perfectly fine. I just have to be careful about the fact that the way I measure lengths and angles changes, right? If I'm in Africa versus, northern Russia here, essentially distances up top are smaller than distances down in the bottom. And so what that means is that lengths and angles change as a function of where you are. And that's essentially captured by this inner product G, right? So the Riemannian inner product is a function at every point P that takes in two tangent vectors and outputs a real number. It's symmetric and bilinear, basically a positive definite form here. And again, the way I should think about it is just at every point, it gives you a different way to measure angles and lengths. So one simple example of Riemannian manifold is the Poincare disk, where essentially what we do is the topology is still just given by a disk, right? Like the interior of a circle, like what you see on the left-hand side here. But what we're going to do is, in this case, the Poincare disk does not mess with angles, but it does mess with lengths. In particular, it says that I'm going to take the length of a vector and scale it by this factor 1 over 1 minus x squared minus y squared squared. So if you think about that denominator here, right, as x and y get close to the outside of the disk, right, 1 minus x squared minus y squared gets close to 0. So I'm dividing by a small number. So in other words, I amplify the metric as I go farther and farther out on the disk. Now, why would I want to do that? Well, in effect, this is a model for a hyperbolic surface, even though I've drawn it flat in the plane. I think MC Escher was good at drawing these sorts of things, what you see on the slide here. But really, you should think of it more like a potato chip, right? A potato chip kind of has more surface area around the outside than it does in the interior, and that's what's getting reflected by that 1 over 1 minus x squared minus y squared factor there. So again, that's the basic trick in Riemannian geometry, is that I'm going to replace the dot product function with a new one, which acts pointwise in different fashion. And in this case, for example, it kind of stretches out vectors depending on where I am. So this example is one small one. Here's another example in computer graphics. I think this is kind of a fun one, especially because it's from my own research. Remember that a common task is parametrization, which is to take a 3D model and just map it into the plane. So one thing that I can do is look at the manifold of all possible parametrizations of a given 3D model. So for instance, here we have this parametrization of the cow. And if I just take every vertex of this triangle mesh and I place it onto the plane, well, then what I get is a vector in r to the 2v, which is the position of every possible vertex of this parametrization. Now, what is the tangent space here? Well, you can think of it as like little perturbations to some parametrization of my manifold here. And essentially, what the Riemannian metric allows me to do is to measure what perturbations actually affect a parametrization. So for example, if I rotate this cow rug, well, nothing really changes from the perspective of parametrization, right? It's the same parametrization if I translate or rotate. It only changes if I like shift or deform it somehow. And so actually in this little piece of research, we defined a different Riemannian metric on the tangent space to the set of surface parametrizations, which can be used to define a Riemannian optimization algorithm that converges faster than the one that you would get just doing gradient descent. So I'll refer you to that paper for some details. So anyway, if we go back to the more abstract picture, remember that now we have, if I have a local parametrization of my manifold, then what I end up with is like an n by n matrix at every point, which is how to take inner products. And there's an interesting thing that happens, which is that essentially our gradient vector direction depends on our choice of Riemannian metric. That is to say that if we change our ways of measuring lengths and angles, then our directions of steepest descent actually change. And let's actually see why that is. So let's move this out of the way a little bit. So let's say that I have a local parametrization of some manifold. So here maybe is Rn. Here's a parametrization phi, and here's a manifold M, which is, I guess n-dimensional the way I've written it here. And I can take two vectors in Rn now. Maybe this is V and this is W. And essentially, here's the basic idea. I actually have two different inner products. That I could use to compare V and W. Well, I have many inner products, but two that are suggested from this, this picture here, right? One of them is just the Euclidean inner product, which is just given, if I write V and W in coordinates, I can just say, V transpose W or, V dot W, whatever. Essentially, I'm using the geometry of Rn. But phi here, right, so maybe it takes the origin to some point P, and here's the tangent plane. If phi is not an isometry, then it can actually take V and W and it could like shear them, or it could scale them, or whatever. So we have a different inner product, which is inherited from M. And essentially, what I could do is say, okay, well, I could, if V and W are centered at the origin here, I could take d phi 0 of V, right? So that's like the image of V under our mapping here. And I can do the same thing with W and essentially take their inner product in whatever space that M is in, right? D. And here's the thing. These two notions of inner product do not have to agree. One is a dot product upstairs, where I take v and w and push them into tangent vectors on our manifold and then take their dot product. That's option 2. And option 1 is just to take their dot product up here. So one thing I can do is I can sort of pull back the option 2 here to put, at least locally, a Riemannian inner product on Rn. By the way, when I say Rn, I really mean in some local neighborhood of the origin, right? I don't need the whole plane to get, or the whole Rn here to get mapped to the manifold. That's fine. And how could I do that? Well, if I have some point x, and so x gets mapped here to like phi of x, right? Then I can put a little inner product that lives on, tangent vectors at x as follows. I can say, okay, well, gx at v comma w, what I'm going to do is map them through phi and then take their inner product, right? So I have d phi x at v dot product d phi at x of w. So notice that this inner product changes as a function of where you are. Okay, so right, so in particular, if I take v and w to be the standard basis, then I can define a matrix Gij, which is really a function of x, which is just the Gx evaluated Ei, Ej. And notice that this is a semi-definite, or actually a positive definite matrix, assuming that phi is a local parametrization. So so there's one thing, right? So essentially what did I do? I took, in this case, an embedded manifold with a local parametrization, and I can pull back the metric of our embedded manifold to Rn and kind of put a little Riemannian structure locally here. That's one of many ways to obtain a Riemannian structure, incidentally. So now here's our observation, which is that essentially the steepest descent direction, I'll say SD direction, depends on the inner product. So what do I mean by that? Well, let's now add another thing to our picture, which is we're going to paint onto our manifold like an objective function for our optimization routine, right? Because remember, at the end of the day, we're trying to like optimize a function on a manifold. So I have some f, which maps from your manifold just into the real numbers, and my task at the end of the day is to minimize f. Okay, so hopefully these kinds of differential geometry style pictures are beginning to be intuitive to you guys. Okay, so one thing that I could do is the following. Well, I can compose phi and f locally, like that. I'm going to call this map f bar. Okay, so I'll say that f bar of x I can define to be f of phi of x, right? So I kind of take a point, I map it to my manifold, and I map it downstairs. Well, what can I do? I can write a first order Taylor series as follows. I can say, okay, well, in that case, f bar of x is roughly equal to f bar of x0 plus, well, actually, you know what I'm going to do instead? I'm going to say f bar of x, sorry, x0 plus delta. Hopefully that's okay. So what is that? Well, that's f bar of x0 plus delta dot product, the gradient, I'll say specifically on Rn of f bar of x0 plus higher order stuff. Okay, so, well, if you think about it here, there's an inner product going on, right? This is the dot product in Rn. And so why do we talk about this direction here as being the direction of steepest ascent? Well, one way to motivate it is that it's really a byproduct of Cauchy-Schwarz, right? Which says the following, right? It says that this number, delta transpose, delta dot product really, of f bar here, well, this is less than or equal to the norm of delta times the norm of this gradient. Like that, with equality exactly when these two things are, parallel, or maybe equal to one another. So, this is one way to understand the steepest descent idea, which is that essentially we're choosing the direction that saturates this upper bound here. But here's kind of an interesting observation, which is that, well, I can actually kind of wedge the metric matrix here in an interesting way. I can do the following. I can say, okay, well, this is f bar of x naught plus delta transpose. And now here's going to be my little trick, is that I'm just going to say, okay, well, I can put the metric matrix, we'll say g x naught, maybe like that, times g x naught inverse, right? This is just the identity, times gradient like that. X. Okay, so why on earth would I do that? Well, now effectively what I've done is I've pulled back the metric from M, and I'm using it back here. And so at the end of the day, if I parenthesize this expression in a different fashion, it's kind of like that, right, then I can understand this as follows. So this is f bar of x naught plus g at x naught evaluated at delta, comma, and here's the thing, it's not the gradient anymore, it's the gradient pre-multiplied by g inverse. Now, what is this vector? Well, if you go back to our lecture where we define what it means to take the gradient of a function on a manifold, what you'll end up seeing is that essentially this vector here is obtained by taking the gradient of f using the metric of m, so like forgetting that there's this function phi at all, and then just taking the pre-image of that gradient direction under phi. So this is some other notion of gradient direction that lives in our local parametrization. It lives in Rn, but it is the gradient direction of the function on the manifold after you push it forward by d phi, rather than the gradient of the function pulled back to Rn, which is option 1. So we'll call this option 2, where essentially we can say, okay, well, our manifold gradient direction pulled back to Rn here of f bar is going to be g inverse times our classical gradient for Rn. So at the end of the day, why bother doing all this math? Essentially what it says is that if I'm on a Riemannian manifold, then when I compute gradients of functions, well, how can I do it? I could pull the function back to local coordinates, that's perfectly fine, and compute the gradient as if it were a function on Rn. But if I want my gradient to take into account that it doesn't need to be the steepest descent direction here, but rather on our curved space, the way that I do that is I take that vector and I pre-multiply it by this g inverse, where g is the matrix written here. Okay, so this already suggests that our optimization algorithm is a little different, right? We have a different notion of gradient than we had before, basically by incorporating a Riemannian metric here. Let me clean this out a little bit. Okay, so hopefully you now have an idea of what it means to compute a gradient on a Riemannian manifold. So essentially, Riemannian gradient descent looks exactly the same. I mean, you just have to define geodesics on a Riemannian manifold, which you can do using the geodesic ODE. If you check the one that we wrote down in class a long time ago, it's sort of well-defined in this case as well. Up to a bit of like kind of replacing that, the velocity of your curve projected onto the tangent plane now looks like covariant derivative. And so essentially Riemannian gradient descent, if you see that term, is nothing more than really preconditioning your gradient with the inverse of the metric matrix and maybe replacing straight lines with an interesting curved path. Now, this is obviously an extremely superficial picture, and there are many interesting extensions of this basic first-order optimization technique. So, for example, you could incorporate line search, where essentially you choose your alpha sub k in a careful fashion, and there exist, for example, sufficient decrease conditions to make sure that alpha isn't so small that you're not making any progress, but at the same time, if you choose an alpha that's so big that f increases, then you haven't done anybody any favors. And an even more kind of non-trivial version of this algorithm, which I'm going to omit for now, we might come back later in this course depending on if we have time or not, is that you can define an analogy of Newton's method on a curved manifold. This becomes a little bit tricky because in order to define Newton's method, you need to be able to compute Hessians. And in this class, we've talked about how to compute gradients of functions on manifolds, but computing Hessians, which are kind of like matrices that now act on the tangent space, incorporates a covariant derivative, so it's a bit tough to define. I'll see, if there's sufficient interest among the students, we can kind of return to this topic later. Another interesting extension, just to call out a few kind of fun areas in the world of manifold optimization, is that you can actually define some notions of convexity. So just the same as convex optimization somehow makes a lot of optimization problems easier to work with, or at least to prove theorems about, there's some notion of convexity that makes sense on curved domains, especially when they have negative curvature or when they have relatively small radius. So you can define a geodesically convex set to be a set where, essentially between every pair of points, the entire geodesic from one point to the other is also inside of that set. And you can similarly define geodesic convex functions. And then many of the nice properties that we know and love from convex optimization, like a lack of local minima, kind of extend to this case without a whole lot of change. So to get started, I thought essentially I'd spend some significant time in our discussion today just deriving some manifold optimization algorithms for some practical problems so that you can understand the sorts of calculations that go into it. So to start with, we can talk about one really simple space that shows up all over the place, which is the unit sphere. This is notation that always trips people up, which is that Sn minus 1 is embedded in Rn, and it's the set of all unit length vectors. So the n minus 1 here is to denote the fact that your sphere is n minus 1 dimensional. For example, S2 is embedded in 3D, right, because it's a two-dimensional surface. So what is the tangent plane to the sphere? Well, there are many different ways to figure that out, but essentially at a point P, the tangent space of the sphere is nothing more than the set of vectors whose dot product with P is equal to 0. So this is actually just a corollary of a theorem that we proved a long time ago when we discussed the Frenet frame. Remember that if I draw a curve on the unit sphere, when I look at its tangent, so in other words, a curve of unit length vectors, then the curve is necessarily orthogonal to its tangent. We use that to derive the fact that the tangent and the normal of the curve are orthogonal to one another. Well, that's essentially what's defining the tangent space of the sphere here, right? So if I have, maybe I'll draw a quick picture here. So if this is my sphere, here's my center point. So here's a point P. Okay, well, what is the tangent plane? It's all vectors that are orthogonal to the surface, and in this case, they're also orthogonal to P, right? That's essentially what that's saying. So what do? If we want to compute the gradient of a function, and our function only exists on the sphere, then we have to use the machinery that we've talked about in earlier lectures. One pretty common scenario is that I can take my objective function on the sphere and really view it as a restriction of an objective function that exists on all of Rn. So for example, I don't know, maybe I want to, minimize 1/2 x transpose Ax subject to x being in Sn minus 1. Well, this objective function, of course, is actually well defined. This is over x, of course. This objective function is well defined on all of Rn, not just on the sphere, right? And so in this particular case, one thing that you can prove quite easily is that if you want the intrinsic gradient of your function, you can obtain it by computing the extrinsic gradient, like just the gradient of this objective function if there were no manifold constraint, and then projecting it onto the tangent plane. So for instance, remember that the tangent plane to at a point P to my Sn minus 1 is a set of V with the property that V dot product with P is equal to 0. So this forms some linear subspace, right? The space of all things orthogonal to P here. So notice that I minus PP transpose is the projection onto that space, right? So the intrinsic gradient of a function that exists on all of Rn can be obtained by differentiating that function on Rn and just projecting it onto the tangent plane. So remember, we need two ingredients to define a manifold optimization algorithm. One of them is an intrinsic gradient. So for example, if f is defined on all of Rn, that's how you might compute it. The other one is a retraction. And here are two potential options for a retraction. Both of these are perfectly valid in practice. And these correspond to the actual exponential map or the projection, right? So here's the basic difference. So here's my sphere again. Now it's in 3D. You can tell because I drew that little belt around it. So if I have a point here, then the exponential map defines just a curve that actually moves along the manifold to the next point. And this just turns out to be the correct geodesic formula. I'll let you guys work this out at home. Here's a retraction. By the way, we often use R for retraction. I think earlier in the slides I used the word retraction. But essentially, what is this formula doing? It's like saying, take a gradient step off of the sphere and then project it back orthogonally. You can see that these two things don't agree, but locally they do. So like in a small neighborhood, these are more or less the same, as a function of v, right? This is our vector v. But then as v gets bigger and bigger and bigger, they can begin to disagree. So for example, if v is like really humongous, when I project it back, I'm still going to get a point that's actually not so far from where I started. Whereas if v is really big, and that's in the projection, which is a retraction. Whereas if v is really big and I follow the exponential map, then maybe I end up like looping around the sphere a bunch of times. So that would be just some illustration of a difference. So now you can define optimization algorithms on the sphere. I don't think those are super exciting. I think many of you guys could have derived these at home. So instead, we're going to do one that's a little more interesting. Now, that more interesting manifold is one that we can call the Stifle Manifold. Its mathematical notation is Vk of Rn, and it's defined like what I show you on the right-hand side. Now, this is an example of a matrix manifold, for obvious reasons. It's a manifold of matrices. And in particular, it's the set of n by k matrices with the property that if x is my matrix, then x transpose x is equal to the identity. Now, initially, this feels like orthogonal matrices, but notice that I haven't constrained n to equal k. So for example, if k equals 1, this would be the unit sphere, right? Because essentially it would say that, the vector dot product with itself is equal to 1. More generally, this is the manifold of matrices with k orthonormal columns in Rn. This is known as the Stifle manifold. So I thought, for fun, we could derive what it means to have a tangent space on this manifold, as well as talk about a retraction operator on this space, because it turns out that the exponential map is not so easy to work with. And again, once we have a tangent space and a way to project onto the tangent space, as well as a retraction, now we can optimize on this manifold using manifold gradient descent, which is pretty cool, because problems like principal component analysis can be understood as optimizations on the Stifle manifold. Okay, so let's get started with that. So as usual, I'll hide our formula on the upper right here. So the first ingredient that we're going to need is the tangent space of our manifold. Now, there are many different ways to talk about tangent spaces. I I think in this case we can actually work with the very first definition that we ever had in 838 of a tangent space, which is that it's like the space of initial velocities of curves. So in particular, we can trace out a curve, and maybe, I don't know, we'll call it x of t, where for every single t, this is inside of this space, vk of Rn. Okay, well then by definition, for all t, what do we know? Well, we know this relationship on the upper right? We know x transpose x is equal to the identity. So I can write x of t transpose x of t is identically equal to I k by k. So what are we going to do? Well, remember that we want to figure out the tangent space, which usually involves derivatives of curves. So let's differentiate both sides of this expression. And what am I going to get? Well, if I differentiate, then I'll get x of t transpose x prime of t. This is just the product rule, yeah, plus x prime of t transpose x of t. I will be a little careful because we're in matrix land, so things aren't commutative anymore. And the derivative of the identity matrix, of course, is equal to 0. Okay, and moreover, we can, if we take any curve whose tangent satisfies this relationship, you can kind of work backward, and you'll observe very quickly that, if it starts out satisfying this condition, then it remains satisfying this condition. So in other words, essentially what we just showed is that the tangent space at a matrix X to our manifold, which is Vk of Rn, what is it equal to? Well, it's equal to the set of matrices. I'm going to do something brave. I'm going to use a Greek letter that I can never draw. Xi, with the property that X transpose Xi, for me, Xi is basically a big pile of squiggles. We're just going to roll with that today. Plus Xi transpose X is equal to 0. And notice that this is a linear condition on Xi, which makes sense, right? Because you want the tangent space to be linear for a manifold. Now, the next thing that we can do is define a retraction here. And one thing you can do is just kind of guess one and then check that it actually satisfies the properties that you need. So in order to define a manifold optimization technique, you need some retraction formula. And here's one. And so what I'm going to do is just give it to you. And we're going to check and double check that this thing is actually a retraction. So what I'm going to say is that the retraction at x is kind of like exponential map, but now it doesn't have to be the actual exponential map. In the Xi direction, we're going to define it to be x plus Xi times, I'm sorry, I'm looking at my notes, the identity plus Xi transpose Xi, all of this to the minus 1/2. Okay, so this seems like a little bit of a crazy formula, but let's see that it actually satisfies the properties that we need. So what do we need for a retraction? We need two properties. The first is that for any Xi, when I input Xi at Rx, I get some point on my manifold, right? I better not leave my space. And then the other one is that to first order, it agrees with the exponential map. So let's check these two properties. So the first one is that it's on the manifold. So essentially, what do I need to check? I need to check that Rx of Xi satisfies this expression up here, right? That x transpose x is equal to I. So I need to do the following. Rx of Xi transpose Rx of Xi. Okay, well, what is that equal to? Well, it's the transpose of this thing. This is symmetric matrix, so it's I plus Xi transpose Xi minus 1/2. Okay, transpose. So now we have x plus Xi transpose times x plus Xi plus I plus I transpose Xi to the minus 1/2. like that. Okay, so initially it looks like we're in trouble, right? I mean, there's 4 terms here. These two don't have a square root in them. But here's the thing. Let's say that I expand the square here. What am I going to get? Well, I'll have x transpose x. But what is x transpose x? It's the identity. Okay, so that's kind of cool. Plus x xi plus xi transpose x. But that's 0 by definition of the tangent plane. So all the cross terms, they actually cancel out because xi is in the tangent plane by definition. Plus xi transpose xi. And now you can see how we define this retraction. It's essentially by just noticing that when you expand this square, you get this nice identity plus xi transpose xi. Okay, but take a look. So I have identity plus xi transpose xi. Now I have the same thing to the -1/2 on the right-hand side, and the same thing to the -1/2 on the left-hand side. So when I multiply all these things together, well, I just get the identity, right? Check. Put my victory mark here. Okay, so the second property that I need to show, B here, is that it differentially agrees with the exponential map. So I need that it agrees with the exponential map at x for small xi, right? Okay. So here's going to be our trick. So first of all, by the way, I guess I didn't say it explicitly, but we can put a metric on this set of matrices here, I guess this set of matrices here, by just restricting the metric of Rn by k, right? Just using the Euclidean metric. That's perfectly fine. Okay, so now what do we need to do? Well, there's a lot of different ways to do it. I'm going to choose one here, which is I'll take, again, a curve on my manifold. Well, now in a curve in my tangent space, actually. Right, so I'm going to say that I'm going to have a whole set of tangent vectors at x with xi prime of 0 equals, oh, I'm sorry, with xi of 0 equals 0. And why is that? Why is this going to be useful? Well, remember that essentially I have 2 different functions. I have the exponential map and I have my retraction, and I want them to agree, right? So here's my tangent plane. And essentially they need to agree to first order, meaning that if I draw some curve through the origin here, 0, then essentially the first term in the Taylor series for x evaluated in this direction should be the same as the first term in the Taylor series for our retraction. That's what we're trying to argue. An equivalent way to put that is that the differential of our retraction looks like the identity map at 0. That's what we're going to show. Okay, so here's how we can do that. Well, now we can compute d over dt of our retraction at x of xi of t. It's going to be just a giant chain rule, as usual here. Okay, so how can we do that? Well, we can use the product rule. So in the first time that we do that, if we do the product rule, on the left term, x is constant, and we just get a xi prime. So we have the following, which is xi prime times the identity matrix plus xi transpose. These are getting progressively messier. Oh, I'm sorry, xi transpose xi. Ah, my bad. All that to the -1/2. Okay, plus x plus xi times d over dt of this crazy thing here. Identity plus xi transpose xi to the -1/2. Okay, so now I'm going to make use of a fun fact that I'm going to let you convince yourself of at home, which is the following. Essentially, here's our kind of useful piece of information here, is that the square root of 1 plus t squared is equal to, if I just compute the Taylor series, 1 plus t squared over 2 plus big O of t to the 4th. This is just a Taylor series calculation that you can all do at home, I think, /hope. Okay, So why is that useful? Well, what we're going to do is we're going to take this derivative here, this d over dt term, and by essentially a matrix function argument, what we can see is that this ends up looking like, well, d over dt of the expression here, which if I put in our sort of matrix Taylor series is I plus 1/2 xi transpose xi, right? That's like the t squared over 2, plus some fourth order terms in xi. Those actually don't matter. Because what happens when I compute fourth order terms? Well, they still end up with at least one factor of xi here. Okay. So if I differentiate that with respect to time, right, really this is like big O of xi to the fourth in some sense, or like all the possible fourth power combinations of elements here. What do I get? Well, the identity doesn't change. So I get 1/2 xi transpose xi prime transpose xi plus 1/2 xi transpose xi prime plus and so on. But like, here's the thing that matters. The leading term went away because I differentiated with respect to t. There is no first order term. The next is second order. And so in particular, in front of each one of these things is some factor of xi, and that continues in our higher order terms as well. So at the end of the day, if I put in t equals 0, like that, well, what am I going to get? Well, the first term, I'll get xi prime of 0. That's fine. So that's like some tangent vector here, times the identity plus 0. So that's fine. Second term, I'll get x plus xi, so which is whatever it is, I guess x plus 0, multiplied by this thing. But every single term in this expression has a xi factor. So it's just plus 0 because we know that xi of 0 is equal to 0. Okay, so what did I show? Well, in effect, what I just showed is that d of the retraction at x at 0 is just equal to the identity, which is what I wanted to show. Essentially what it's saying is that my retraction agrees with the exponential map, at least right at the center. Away from it might not be, but the first order kind of Taylor series term here is just giving me back the tangent vector, and since I'm using the inner product from Euclidean space, like the n by k here, I'm good. Okay, so what did we just do here? We started with the Stifle manifold, Vk upstairs here. We derived its tangent space, which is the set of matrices that satisfy this condition here. And this is a linear condition, and notice that the tangent space varies depending on what x you put in. So it actually is a curved manifold embedded in this space of all n by k matrices. That's what makes our problem interesting. And we verified that this function Rx here is indeed a retraction, meaning that we now have a way of doing gradient descent on this manifold, where what do? We can project things onto this linear space at every step of gradient descent to compute an intrinsic gradient. And then we put that intrinsic gradient into this formula as xi to take our gradient step forward in our optimization algorithm. So again, to summarize in a cleaner, non-handwriting kind of way here, here is our tangent space and our retraction, and those are the two elements that we need to derive a manifold optimization technique. Okay, so there's our first example of doing some real-life calculations when it comes to doing manifold optimization. Notice that we were able to do things like define a retraction, which was a more general object than an exponential map, and that really these are the two ingredients we need to now optimize whatever objective function we feel like on this Stifle manifold. Now, as a more kind of real-life example, I thought I would work through an example which is basically minimizing the Rayleigh quotient. So given a symmetric matrix A, we can try to minimize the objective that I give you on the slide here. Now, this turns out to be a problem that we all know and love, right? So in particular, notice that I'll kind of do our to-dos in the same order that's listed on the screen here, we can relate this problem to an eigenproblem. So let's say that I write this in the sort of classical constrained optimization way, right? Then my Lagrangian would be a function of x and lambda, and it would be 1/2 x transpose ax. And now we're in the unit sphere, so maybe we do the following, which is we say lambda. And just for fun, rather than saying the norm of x equals 1, maybe I'll say the half the norm of x is equal to 1/2, like this. And the norm squared, right? So all these are equivalent. Okay, so there's my Lagrangian for my optimization problem. If I take the derivative with respect to x and set it equal to 0, right? That's my Lagrange multiplier condition. Like that. What do I get? Well, the gradient of the first term is just ax. And gradient of the second term, well, the gradient of 1/2 the norm of x squared is just x, so it's minus lambda x. So in other words, you get that ax equals lambda x. And you can actually check here that the optimal objective value ends up being lambda, right? Because it's, or 1/2 lambda, I guess, because x transpose ax is now x transpose lambda x. The norm of x is 1, so I'm just left with 1/2 lambda. Okay, so solving this minimization problem is equivalent to finding the minimum eigenvalue of A, which is kind of nice. Now, let's say that I wanted to solve this not with like eigenvalue iteration or something like that, but with a manifold optimization algorithm, right? That's sort of bullet point number 2 here. Well, I can do that pretty straightforwardly. So in particular, remember that I can get my intrinsic gradient, we actually already argued in this lecture, by taking my extrinsic gradient and projecting it onto the unit sphere. So in this case, the gradient with respect to Sn minus 1 of my objective here, 1/2 x transpose ax. Remember how I can do that when I have a function that's defined on all of space. I can take the gradient of the inside, so that's ax, and then project it back onto the tangent plane. So what I'm going to get is identity minus xx transpose times ax, like that. So that is, at the end of the day, the intrinsic gradient of my technique. So if I want to write down a first-order algorithm for optimizing this particular problem, well, it's pretty straightforward, right? So I have sort of 2 options, right? I can, compute vk, which is going to be, the current intrinsic gradient, like that. And now to get the next iterate, well, I kind of have 2 options, right? I could say xk plus 1 is the exponential map at xk of vk, or xk plus 1 is maybe the retraction at xk of vk. And conveniently, I gave you formulas for both. Oops, I'm sorry, these shouldn't be vk. It should be minus vk times alpha k. Sorry about that. Right, and so conveniently, if you remember from earlier in our lecture, I actually gave you both a retraction and an exponential map for the unit sphere. You might ask which one is better in practice, and my bet is probably the exponential map, but it does require computing cosine and sine, which takes a little bit of time. And really, I think the guarantees are the same for these 2 objects. For kind of positively sized steps, because the gradient only tells you local information. But interestingly, actually, there's an interesting extension of this technique, which is to actually refine an eigenvector estimate. This is an interesting algorithm that people actually use in practice. It turns out that sometimes you get eigenvectors from this kind of technique that can be a little bit inaccurate, even more so if you use eigenvalue iteration. So one thing that people have found actually can help make this better in practice is to say, okay, for instance, if A here is a indefinite matrix, then some x's will be saddle points, some x's will be local mins, and some x's will be local maxes. Once I get in the neighborhood of eigenvalue that I want, maybe I define a new problem f tilde of x, which is equal to the norm of the intrinsic gradient of my original objective x transpose ax, like that. Which essentially, what this is doing is turning saddle points of our problem into local minima. So like, for instance, let's say that I wanted to target an eigenvalue that wasn't the smallest possible eigenvalue, but like the biggest one. That would still be a local minimum of this problem. So this is an interesting kind of extension of what I've written on the top. And it's a local minimum because, of course, the gradient is equal to 0 at any of these things. And now I'm taking the norm, so that's the smallest possible value. Okay, well, I can write a manifold optimization problem for this thing that refines any eigenvector estimate, even if it's like the estimate of the third out of the 53 eigenvectors of a 53 by 53 matrix. So how do I do that? Well, again, what is this thing? Well, it's equal to the norm of the projection onto the tangent plane at x of, in this case, just ax again. Okay, so, well, what is this function? Well, remember that the projection is just this matrix here, right? This is px. Okay, so when I kind of plug that in and turn the crank a little bit, what I get is x transpose a transpose px ax, right? That's just by expanding the square here. And of course, I can plug in our formula for p if I wanted to, and what I'll get is x transpose a squared, or if a is symmetric, then a transpose x, whatever, minus x transpose ax squared, which is an interesting kind of new objective function whose local minima are exactly the eigenvectors of our matrix. All the eigenvectors now, not just the smallest one. Okay, well, if I compute the gradient of this thing, what do I get? Well, you know, again, I have to be really careful when I compute intrinsic gradient of f tilde, because I have to compute the gradient of this expression and then basically just I have to keep projecting it. So what I'll end up getting, I can always be safe and put this projection here. And then when I differentiate the inside, well, I'm going to get 2 times a squared x. So I'm going to go ahead and factor that 2 out, minus, and then you get a second 2, x transpose x. Oh, oops. Wait, x transpose times a times x. Right, and this comes from 2. We get an x transpose ax here, times the derivative of x transpose ax, which is ax. Woof. Okay, so from here, now I have the intrinsic gradient. Well, I can once again use the same optimization algorithm with a new v. And what this gives me is a technique that starts with some estimate of an eigenvector, and then just by doing kind of local gradient descent on this kind of funny fourth order function here, or I guess third order, can make it better. So what's our story here? Essentially, we started with an optimization problem, which we argued was equivalent to computing the eigenvector corresponding to the minimum eigenvalue of A. And now 2 and 3 here are just filling in the details of how we can do that, right? So to compute the intrinsic gradient, we computed the true gradient of our objective function, which is just a times x, and then projected onto the tangent plane. And now our first order algorithm is really simple. It just alternates between compute the gradient and then put it into either the exponential map or the retraction, and we define one of each in a previous slide here. And now for a fun extension of this technique, not only can we use it to just compute the minimum eigenvalue of a matrix A, right? That's this first kind of setup here. But now we define this new objective function, which amusingly is actually the norm of the intrinsic gradient of our previous problem. And why is that? Because we know that this thing is equal to 0 anytime that x is an eigenvector. And so this norm equals 0 at any eigenvector of A. So now when we expand this out, compute the gradient, then refining an eigenvector estimate is as simple as plugging in a different gradient into the same algorithm in number 3. So this is just another example of a manifold optimization algorithm. And the reason that I say it's manifold optimization is notice that every single iterate xk here, by definition, is a unit vector. We never leave this constraint set Sn minus 1. Okay, so there's an example end-to-end of how to derive a simple manifold optimization algorithm. So in the slides, I mentioned a second interesting manifold optimization algorithm, which works on the Stifle manifold. Now, we already did the kind of interesting parts of this algorithm because we, already derived the tangent space. Since I'm a little low on time in our lecture, I think I'll skip it. If you guys are interested and would like, I can either write it up or essentially give a short extra lecture segment to derive an optimization algorithm on the Stifle manifold for this objective function here. The one thing that's worth noting is that this is actually the PCA problem, the principal component analysis problem. Maybe that's not obvious, but if we think of the columns of this matrix X as PCA vectors and my data as being in the matrix A, right, then X transpose A is like the projection of my data onto my lower dimensional basis, and the maximizing is essentially maximizing the correlation between A and X, and you can make that relationship formal by plugging in the SVD of A. Now, the reason why you might want to do that is now I can add other objective terms. So what I challenge you to do at home is to come up with variations of this objective function, which do two different things. One is robust principal component analysis, which is to say that maybe I expect there to be a few outlier columns of A, so maybe I want to encounter some kind of L1 norm in the way that I measure my error. And a different one would be sparse PCA, which wants the entries of A to be close to 0 or equal to 0 if possible. Both of these emit slightly different objective functions that are more general and don't emit nice closed-form solutions like the SVD that we use to solve principal component analysis problems. But in any event, since we're low on time, maybe I'll skip this one and refer you to Abzil's textbook, or I can make an extra lecture segment if you request and fill in the details here. So why do we like these manifold optimization algorithms? Well, there's so many interesting optimization problems that we can solve by just plugging in new objective functions into different matrix manifolds, for example. So the Stifle manifold that we've worked with quite a bit in today's lecture is essentially the manifold of PCA axes, right? It's like the set of orthogonal bases of size k. And so here's this giant table I've included in the slides from a 2015 paper that surveys all of the different objective functions you might put on your matrix, which give you different variations of principal components, like whether you want your principal component axes to be sparse, or you expect your data to have a certain type of noise, or what are some of the other ones here? Maybe you do correlated component analysis, or multidimensional scaling. All of these things are just variations of PCA. So you have kind of two options. Either you can cook up your own bespoke optimization algorithm for each new one, which does keep optimization people in business, but is a lot of work. Or you can use essentially just the gradient of whatever your favorite PCA objective function is, plugged into this general first-order method we've written down, and out comes a general algorithm for nonlinear PCA with different regularizers attached to it. Now, there's a whole set of techniques specifically for efficient semi-definite programming that work on different manifolds of matrices. It turns out that the manifold of semi-definite matrices has its own nice Rimanian structure, and you can use that to derive SDP algorithms, which is important because SDPs are very hard to solve in practice. This is an area of modern research in theory and in practice, and there's some really interesting research papers, including the ones that I've pointed to here, that give you different nonlinear programming algorithms that actually can provably give you sort of the result that you want. In fact, one really simple one is this Montero technique, which basically raises semi-definite matrix as X transpose X for a more general matrix X. That's one way to write down that manifold. But then you have to be a little bit careful because you're working in a nonlinear, non-convex space anymore. There are interesting problems involving embedding and distance completion that can be written this way. Low rank matrix completion can be written in Riemannian optimization. Synchronization, so like I have a bunch of rotation angles that are kind of relative motions, maybe from one camera pose to another, and I want to put them all on one common frame or sort of different variations of that problem. Essentially, I'll just refer you guys to the papers I've pointed to in the slides for many, many different examples of different manifolds that show up in practice for computational problems. And now, basically, you're equipped with the machinery you need to derive simple algorithms and use that ManOpt algorithm or ManOpt software to solve them in practice. If you want to see a ton of different examples, I would refer you to the ManOpt code base, which actually has a ton of really nice examples that are completely worked out, including a piece of code so that you can solve these problems in practice. So in any event, we're getting toward the end of 6838, and my mission right now is just to give you a big grab bag of really interesting new frontiers in applied geometry. One of them, which really involves basically applied Riemannian geometry, involves optimization on interesting curved spaces or manifolds. Now today we had pretty much a very superficial introduction to this field, but hopefully I've convinced you that oftentimes the variables in optimization problems that we care about live on some curved manifold, like the Stifle manifold or a sphere. And once we know that, then by using either the exponential map or this new object that we defined today called a retraction, we can basically cook up gradients, or rather analogs of gradient descent that never leave our constraint set, which is valuable both in theory and in practice. Also notice that these algorithms really aren't so hard to implement. It's just a bunch of carefully designed formulas. So with that, I'll let you guys explore this topic more on your own, and I will see you next time.